Okay, so we actually started with the frequency meters yesterday, and we have different types of frequency meters. So the first one that we studied was the mechanical resonance type, and in this you have simply a reed, that's a mechanical part that will come, and these reeds will be vibrating as the windings wound around this electromagnet will be excited. So one correction here, that the natural frequency has to be equal to the twice the supply frequency for the resonance to take place. So once you have the resonance, the most vibrating reed will actually indicate the frequency of the supply voltage. So then we start with the electrical resonance type. So you have two types of electrical resonance type frequency meters. One is the ferrodynamic type that we studied. You simply have the circuit with a moving coil and one fixed coil. The fixed coil is excited, that will cause the torque, that will induce torque in the moving coil depending upon the nature of impedance of this moving coil, whether it's purely resistive, inductive or capacitive. So accordingly, as the at a purely resistive load, a resonance will be set, and we know at resonance frequency is nothing but 1 by 2 pi under root of LC. So we'll move on to the second type of electrical resonance device, electrical resonance type, and that is that we actually have put as another type also, electrodynamometer type. So this is another electrical resonance configuration. So that means basically an electrical resonance will be set. So we have this construction here. So this basically here represents an electrodynamometer type frequency meter. So construction wise, you have again the moving coil and the fixed coils, but here you have two fixed coils. Both coils are in series with inductance and a capacitance. You have L1 and C1 here, and you have L2 and C2 here. The difference will be that this will be, say for example, the resonant frequency of this circuit, resonant frequency F1 on this side, it will be less than the as I was saying, the resonant frequency F1 of this side of the circuit F1, it will be less than the, say for example, we have this device will be measuring between a range of 40 Hz and 60 Hz. So lower end of the scale, I'll say simply the lower measurement, it will be less than the lower measurement of the frequency that this particular circuit can measure. While as the resonant frequency F2 of this side will be higher than the upper measurement or the higher measurement of the frequency scale. F1 is the resonant frequency of fixed coil 1, F2 is the resonant frequency of fixed coil 2. So both will be in resonance, but they will be at different frequencies. You have to appropriately choose the values of L1, C1 and L2 and C2. F1, we keep L1 and C1 such that F1, the resonant frequency of the fixed coil 1, will be less than the lower side meter reading of this particular device, and resonant frequency F2 is kept such that it will be slightly higher, it's not much less or much low, it will be slightly higher than the upper scale meter reading of this very particular circuit. So you have two fixed coils and you have one moving coil that basically now forms the part of the electrodynamometer. And you have a moving coil that's attached to in a star fashion to these fixed coils. So moving on to the operation of this electrodynamometer. So we have understood that one fixed coil has a different resonant frequency, another fixed coil has another resonant frequency. So this is possible that the fixed coil 1 is more of an inductive in nature and fixed coil 2 is more of a capacitive in nature. The total current that will be flowing through the moving coil is I1 plus I2. I1 is the current flowing through the fixed coil 1, I2 is the current flowing through the fixed coil 2. Since both are connected to the supply voltage to the same end, and the current path flows through the moving coil, so the total current flowing through the moving coil is I1 plus I2. So the torque that will be induced on the moving coil will be actually proportional to the sum of the currents I1 plus I2. Now we need to understand here that individually speaking, I1 will be lagging while as I2 will be leading in nature. So the two torques that will be produced by the individual fixed coils will actually be opposing the effect of each other. So what happens in this case is that the resultant torque will actually now be a function of the frequency of the applied voltage, and hence the meter scale can be calibrated in such a fashion so as to give us the frequency of the circuit. Repeating this, we have for the applied frequency, the circuit of the fixed coil 1 will be operating only above the resonant frequency, whereas for the applied frequencies, the circuit of the fixed coil 2 will be operating only below the resonant frequencies. We have already discussed this, that the resonant frequency of fixed coil 1 is lower than the lower limit, and fixed coil 2 resonant frequency is higher than the upper limit of measurement. So both these, so for the applied frequency, circuit coil 1 will be operating above the resonant frequency. That's why it's inductive in nature, while as the circuit of the fixed coil 2, this circuit is having a much higher resonant frequency, so it's actually operating so within the range of frequencies that this device is measuring, that's actually less than the resonant frequency of fixed coil 2. So that means it will be capacitive in nature. So you have an current I1 that will be lagging the applied voltage, you have current I2 that will be leading the applied voltage. So one fixed coil is inductive, another fixed coil is capacitive in nature. So the torques that will actually be produced now by both these two fixed coils will be acting in opposition to the moving coil. Now this resultant torque will therefore be be a function of the frequency of the applied voltage. So if we can calibrate the scale of this device, we can basically be able to find out the frequency of this from this device. So this meter can be used for measurement of power frequencies and also for monitoring purposes. So this is about electrodynamometer type. Now moving on to the next type of frequency measuring device, that is Weston. So this circuit diagram here, this configuration here basically is shows the detailed construction of a Weston type frequency meter. So first of all, the construction, we have actually two coils here, coil A and coil B. Both are divided into two segments. And these two coils are actually perpendicular to each other. Fine. So you have coil A, this is coil A here, this is coil A here, this is coil B, this is coil B. So you have both coils are divided in two segments, and coil A and coil B, they are perpendicular to each other. Now coil A, you can see this is coil A. It has a resistance Ra in series and an inductance La in parallel. While as coil B, it has an Lb is in series, while as Rb is in parallel. So you have coil A having a series resistance Ra and a parallel reactance La. Coil B has a series inductance Lb and a parallel resistance Rb. And there are other devices, the pivots and the soft and the needle for it's a magnetic needle here that will be used for that will actually give the deflection as per the proportional to the frequency of applied voltage. And also both these two coils are connected to the supply voltage through an inductance L. This series with supply, this is series with coil A, this is parallel with coil A, this is series with coil B, this is parallel with coil B. So this is the construction of this device. Now moving on to the operation of this frequency measurement device. So the operation, you have coils A and coil B, they are 90 degrees to each other. Once you apply the supply voltage, coils current will flow through coil A and coil B, and they will produce a magnetic field. Since the coils are placed 90 degrees to each other, so the magnetic field that they will be producing will also be 90 degrees to each other. Now this magnetic field will actually act upon the magnetic needle. So you have both coils are actually producing their magnetic field, so the resultant magnetic field will actually cause the deflection of the magnetic needle. Now what we do is that we design the values of these resistances, these inductances in this circuit such that the needle will take up a position of 45 degrees to both the coils, right? So at the normal frequency of supply, we choose the values of resistances and inductances in such a fashion such that the total magnetic field generated by these two coils A and B will act upon the needle and set up it at 45 degrees to both the coils. So accordingly at that time we can say that this device has been calibrated to this particular frequency. That's actually the rated frequency of supply voltage. So choose LA, RA, LB, RB such that the magnetic field such that the needle is 45 degrees to both coils. Fine. So this will happen at rated frequency of supply, or you can say at 50 Hertz. So we design the system for the rated supply frequencies in such a fashion. We choose the values of LA, RA, LB, RB, and we make sure that the magnetic needle is set up at 45 degrees to both the coils, and whatever measurement of the pointer is at that time, that will actually be calibrated to 50 Hertz, or the nominal frequency of supply. That can even be 60 Hertz for some countries. Now say for example the frequency of the supply increases beyond its normal value. So what will happen is that the reactances LA and LB will also increase. So but there will be no effect on the resistances. RA and RB do not change with supply frequency, but the reactances LA and LB both will change. So that means LA is increasing, LB is also increasing. LA is but in parallel with voltage coil with coil A, that means voltage impressed across LA will increase. That means voltage impressed in coil A is increasing. That means the current in coil A will increase. While as reactance LB is in series with coil B, as the reactance in coil B increases, the voltage across coil B decreases itself, and the current flowing uh, thus what happens is that the field of the coil A now becomes much more stronger than that applied to coil B. So what will happen is that this will actually cause the motion of the needle, and the needle will tend to align itself towards the axis of coil A. So if the vice versa is happening, if the supply voltage is decreased, LA decreases, LB decreases, that means voltage impressed across coil A decreases, voltage impressed across coil B will be much higher than what is across coil A, so coil B will be carrying more current. So in that case, the magnetic needle will tend to align itself more towards coil B. So you can have the pointer being we are not talking about the magnitude of voltage decreasing, we are talking about the frequency of voltage decreasing or increasing. So when there is a increase or decrease in supply frequency, inductances LA and LB will change. That will cause the voltage impressed across coils A and coil B to change. So if supply frequency is increasing, voltage impressed across coil A will increase. So that means the magnetic needle will tend to align itself towards the axis of coil A. If the supply frequency is decreasing, that means LA and LB will decrease. That means voltage across coil B will be much more larger than across coil A. That means in that case the magnetic field will tend to align the magnetic needle towards the axis of coil B. So with this calibration of the device, we can be able to measure the frequency of the supply voltage. So this is about so we have studied Weston type frequency meter, and now we'll be moving on to the next type, that is the ratiometer type. So first of all, the construction. So this configuration shows the constructional details of the ratiometer type frequency meter. So you can basically see in this there are different coil segments, you have rectifiers, etc., and a capacitor. So at the heart of this particular device, there is what is known as a ratiometer. So this ratiometer has simply two coils, and they will be carrying currents I1 and I2, I1 and I2. The ratio of the currents I1 and I2 will cause a proportional deflection in the pointer. So ratiometer is actually a set of two coils, and they can be aligned at any angle, and the currents flowing through the ratio of the currents flowing through the two coil segments I1 is to I2 will actually cause a proportional deflection of the pointer. That's actually attached to the ratiometer itself. Now these ratiometers are actually supplied with DC currents, and these DC currents are actually obtained from the rectifier bridge diode bridge rectifiers, and they are obviously a diode bridge rectifier is converting an AC voltage to a DC voltage. So I1 and I2 here, they are basically DC currents. So DC currents are flowing through the ratiometer, but we need to measure the frequency of the AC supply. So we are trying to calibrate our device to measure frequency of an AC circuit by first converting it to the DC through DC measurements. Also attached to the rectifier bridge in series are a capacitor C, and to another bridge circuit is a resistance R. So you have capacitance C in series with one bridge rectifier and resistance R in series with another rectifier. So I1 and I2, they are basically DC currents. So moving on to the operation of this device. So what happens is you have current I1. It's a rectified current. It's not also purely DC current. You know that. So I1 will be proportional to 2 pi FVC, fine, and I2 current on the second, the output current of bridge rectifier 2, that will be proportional to V by R. So I1 and I2 are the rectified DC currents. We are not using any mechanism to smooth out these DC currents. So they will produce the magnetic field, a static magnetic field, cause an induced torque, that will cause the deflection of the pointer. Now this deflection of the pointer in this case will be proportional to I1 by I2. Theta will be proportional to I1 by I2. So you have two currents I1 and I2 going through the two coils segments, one fixed coil to the two coil segments of the ratiometer, and accordingly the deflection will be equal to I1 divided by I2. So this instrument basically has a linear scale of frequency, and the ratiometer will be so designed that this deflection of the pointer will be directly proportional to the ratio of the two currents. So it's actually the design of the ratiometer that actually makes the deflection proportional to the ratio of the two currents. In this case, we do not have directly any role of the supply voltage in the deflection. It's actually the DC rectified current that's actually causing the deflection, and since there is no consideration with the magnitude of voltage, there's a wide range of frequency can be applied for this particular device, and this particular meter can measure up to 5000 Hertz of frequency. So you have an AC voltage applied to two DC direct bridge rectifiers through a capacitor in one case and through a resistor in another case. So the deflection, the output currents that will be available to us will be rectified DC output, that will not be purely DC. So you have I1 proportional to 2 pi FVC and you have I2 proportional to V by R. The ratiometer is so designed that the deflection of the pointers now caused because of the static magnetic field of I1 and I2 will cause the pointer to move proportional to the ratio of the two currents I1 and I2. So we have done today the electrodynamometer type, the Weston type, and the ratiometer type. So in the next session, inshallah, we'll do the saturated core type, and also we'll look into something else.